Hello guys, welcome back. We're now continuing our double integrations with polar functions. And so our example here is going to say to set up the integral to find the area enclosed by the cardioid of r equals 1 plus sine of theta. This is actually a pretty straightforward problem to do because the question is asking us to find the area of the entire cardioid and not just a piece of it. So one of the things that I want to remind you guys about is that a cardioid is in the terms of a plus b sine theta or cosine theta, where a and b are actually equal to each other. So in this particular case, we have an understood 1 to be in front of the sine of theta. And so let's really quickly graph this to kind of see what's going on with this problem. So if you guys remember back when we talked about polar curves in BC calculus, we remember that since it's a positive and a sine, our major axis is going to be on the positive y-axis. And then the value, the 1 plus 1, is going to give you 2, which is going to be our first point on that axis. The a value, that's going to be the number without the trig function, is going to be the distance from the pole on the minor axis, so 1 and 1, so negative 1 and 1. And then the difference between the two numbers is going to be our fourth point. But again, for our cardioid, our difference is always going to be 0 because a is always going to be equal to b. So we're going to sketch this little guy really quickly, and this is going to be our cardioid. All right. So the first thing we're going to do is we're going to talk about our bounds. So let's talk about theta for a second. So when you're thinking about theta, you want to figure out, all right, well, how long, remember, it's the whole cardioid, so we're going to start right here. So when theta equals 0, we get a radius of 1, so we start here. So how long, how many theta do we get to get back to the beginning? And so you just have to remember your periods, right? So what is the period of a cardioid? The period of a cardioid is actually going to be 2 pi. Most of our polar coordinates are going to be 2 pi. The exception to an equation would be something like r equals cosine 3 cosine theta. Our radius is going to be from 0, and then any point on the curve is always going to be the expression for 1 plus sine theta. So the radius is our lowest point is at 0, and then as I go around this curve, whatever point that I'm hitting here, it's always going to be this value of whatever 1 plus sine of theta is. So we have enough information now to set up our integral. So we're going to go ahead and integrate from 0 to 2 pi, and then we're going to go from 0 to the function 1 plus sine of theta for our r, and then remember we're going to always do our dA, which is going to be r dr d theta. And so we're done with this question because, again, it's just asking to set it up. And so we'd integrate it, and we would get the area of the cardioid of 1 plus sine of theta. So to make it a little bit more interesting, I thought we would do a little bit more challenging problem. So I want you guys to look at question number 5, where we're asking you guys to evaluate the region of D of sine of theta dA, where D is the region in the first quadrant outside the circle of r equals 2 and inside the cardioid of r equals, and I just distribute the 2 plus 2 cosine of theta, because this is, again, is our traditional way that we write cardioids. So over here to the right-hand side, I've already graphed this for us. So the r equals 2 is just a standard curve where r is equal to 2. And then our equation, again, back to the conversation we just had, since it's positive cosine, our major axis is 4. The 2 plus 2 gives us the distance of 4. The value here of 2 is going to be the length of our minor axis, excuse me, and then the difference of the 2 is going to give us our other point. So notice that the question is asking us to find this in the first quadrant, and again, inside our cardioid, which is the round region, but outside the circle that is our r equals 2. So I would encourage you guys to pause the video for a second and then write out what you think the problem is, and we're going to come back together to discuss this problem. All right, guys, so this was actually a pretty challenging problem as I was writing it out for you all. So let's go ahead and just discuss this a little bit more in detail. So looking back over here at our graph, the first thing we want to talk about is what theta is. And so theta is bounded between 0 and pi over 2, right? So this is our low of theta, which is always at 0 on the x-axis, and we actually go up here to pi over 2, which is actually the intersection point of those two curves. So theta is between 0 to pi over 2. The radius is going to be, well, what are our functions? So on this left-hand side of our region, the radius is always going to be equal to 2. So our lower bound is going to always be equal to 2. And based on example number 4, what we talked about is that if I'm the furthest out of my region here, I'm always on this curve. So my higher bound, my upper bound, is going to be 2 plus 2 cosine of theta. Since I'm already in terms of theta here, right, sine of theta, I don't have to convert that. And then I got my r d theta. And so when we do this, we're going to now integrate our function. Remember, the first thing we're doing, guys, is we're actually integrating with respect to r. So the only variable here is r. Sine of theta is a constant. So that's why we leave sine of theta alone. We integrate r as r squared over 2, and then we evaluate that from 2 to 2 plus 2 cosine of theta d theta. So this is where it gets a little bit of fun, right? So I went ahead again with the 1/2, pull on the outside, and I have 0 to pi over 2. I leave the sine of theta alone for a second, and then I just go ahead and use the fundamental thermocalculus, and I plug in our function here, and then our function here. And so that's where the 2 plus 2 cosine of theta quantity squared minus 4 comes into play. So why this is a little bit more complicated is because I'm going to use u sub in this problem. So I need to use u sub here because there's 2 separate parts. So you may want to go and distribute the sine of theta. So u sub we see right here. And so we're going to change the bounds for this first part. So again, when we get u equals 0, we're going to get 4 for our theta. And then when theta equals pi over 2, we get u is equal to 2. I went ahead and pulled out the negative 1/2 from what you see right here, right? We have that extra negative 2. So that's where the negative 1/2 comes from. But then when we integrate the other side, so I have the 1/2 times the negative 4, which is the negative 2, and then I'm going to integrate. And since I did not use the u sub in this particular part, I'm actually going to leave my bounds alone of 0 to pi over 2 of sine theta d theta. And then we go ahead and start evaluating. So again, this little piece right here is here, negative 1/4. We integrate u squared as u cubed over 3. And we're going to evaluate this from 2 to 4. Notice I didn't flip it this time. I could have changed this from 4 to 2 and taken the negative out. I want you guys to know that we can do this. It's all good. It's legit. And then we integrate sine, which is cosine, negative cosine, which again will change the sign here to a positive 2 cosine of theta, again bounded from 0 to pi over 2. And then when you actually evaluate this, you get the answer of 8 over 3. So this is a little bit more complicated. I think there's a lot of moving parts for this problem. So is it testable? I don't think it's definitely not testable, but it's definitely a good conversation to have while we're in class. So I hope this video made sense, and I will see you guys in the next one. Take care.